So I have one more afterthought here, one more supplemental video lesson, 12.2. I want to say something about reaction energetics, kinetics, thermodynamics, just some hopefully basic, hopefully this is just a review for most of you, but I do want to say something about this. So let's take a look at some diagrams here. So take a look at this and tell me what you think this represents. What type of reaction mechanism is represented here? Is this an energetically favorable reaction or an unfavorable reaction? And why? Is it a fast reaction? Is it a slow reaction? And why? What can you tell me about this? Same questions here. What type of reaction is this? What type of a mechanism? How many steps? Favorable or unfavorable? Slow or fast? Any intermediates? How do you know? What's the big difference between a reaction that this diagram represents versus the first two that you saw? What's the big difference? Is this reaction favorable? How do you know? All right, so if you said that the first diagram represented a one-step reaction mechanism that was energetically favorable, you're absolutely right. And it's because we see that the products are lower in potential energy than the reactants, right? And there's a direct path from reactants to products. If you said that the second diagram represented also a one-step reaction mechanism which was energetically unfavorable, right? Because now products are higher in energy than reactants, you're also right. Finally, in the third diagram, if you said that this represented a two-step reaction mechanism with an intermediate as the main difference between that diagram and the first and the second, you're right again. Let's take a closer look at that last diagram and see if we can identify what these arrows mean, right? We have the, let's read this from left to right. Let's go from left to right, and I want you to see that first gray arrow. What does that first gray arrow represent? If you said that that is the heat of reaction, the delta H reaction, you're more or less correct. It's really technically the free energy, the delta G, not the delta H, but because entropy is generally not a major factor, with exceptions, if you call that the heat of reaction, and if you said that that represented a favorable or negative heat of reaction, you'd be correct, right? What about that second gray arrow, again, going from left to right, the one that measures the distance between the reactant energy level and the top of that orange curve? What does that represent? If you said that's the activation energy, the energy required to push the reactants up to the very top of the energy curve to reach that double dagger transition state or activated complex, you'd be right too. And of course that controls the rate of the reaction, the rate of the forward reaction. We're going from left to right, okay? Of course, the intermediate, there is an intermediate in this two-step reaction mechanism, and that's illustrated where the two curves meet, okay? And then as we go from, as we complete the reaction going in the forward sense and complete step 2, right, we have another minor activation barrier, that's that very small gray arrow, and finally we fall all the way down spontaneously to products, right? If we're looking at the opposite, the reverse reaction, and all reactions are reversible, then that, and we read from right to left, then that big purple double-headed arrow, right, represents the activation energy or barrier for the first step of the reverse reaction. And you can see that's going to be a very slow step because that activation barrier is very, very significant. And of course, what catalysts do, right, is they lower these activation barriers. They do not change the difference in energy between the reactants and the products. That's simply a function of the bonds that are broken in the reactants and the bonds that are made in the products. Okay, and that just can't be changed by a catalyst. A catalyst simply lowers those activation barriers and accelerates the reaction. It accelerates the rate at which a reaction reaches equilibrium. Okay, and of course at chemical equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So given this as background or review, can we identify features of organic reactions that are desirable? Reactions that we'd actually like to spend time on performing in the lab, and our time is valuable. We don't want to set ourselves up for failure. So what do we look for? Well, we generally look for a favorable equilibrium constant, right? Favorable KEQ, favoring products over reactants. We want that equilibrium to be established quickly, so we want the kinetics to be fast. We want to achieve selectivity, and we talked a little bit about chemoselectivity versus regioselectivity versus stereoselectivity. And certainly as you get more advanced in organic chemistry, you're dealing with molecules that are polyfunctional, where more than one functional group can react. And so you want to dial in conditions that focus only on one functional group and leave the others alone. Selectivity, and then a fourth consideration, which we're not going to get into, is can you scale up the reaction? All right, fine, you have achieved the first three here, and you've been able to perform a chemical reaction on 1 gram of reactant. Okay, can you achieve that same efficiency with 1,000 grams, a kilogram of reactant? Is the reaction scalable? Well, what about this first requirement, that the equilibrium be favorable, be much greater than 1? Remember the relationship between the equilibrium constant and the free energy change of reaction. There it is. Let's review. Delta G equals minus RT natural log KEQ. Let's imagine an equilibrium constant of 100, right? 100 to 1 ratio of products to reactants. That's pretty good. So we can actually do the math and figure out what free energy change is associated with, excuse me, an equilibrium constant of 100. It's simply a plug-in exercise. The value of the gas constant, R, is 8.314 joules per mole Kelvin. At 298 Kelvin, which is room temperature, the natural log of 100, right, KEQ is 100, gives us a delta G of minus 11.4 kilojoules per mole, okay? Now that's a delta G, and obviously there is an entropy component to delta G, just to remind you, there it is. But unless the temperatures are very high, right, and unless you're basically losing several gas phase molecules as you go from reactant to product, the entropy contribution is not going to be great, and you can approximate delta G to be approximately delta H. Okay, all right, so let's say that we want a difference in bond energies between the reactants and the products of about 11 kilojoules per mole. Is this achievable? So here we have a table of average bond energies, and the answer is it's certainly achievable, if you have set things up properly. So what we want in our list of desirable reaction parameters and to achieve a desirable equilibrium, right, is we want to be breaking weak bonds in the reactant, right? In other words, we want the cost of bond breaking to be low. And so we want to be breaking bonds like the ones I've identified here that have relatively low bond energies. We'll take a look at some of these. Conversely, we want to be making strong bonds in the product. And I've highlighted some typical strong bonds here. And by the way, take a look at that nitrogen-nitrogen triple bond. At 941 kilojoules per mole, that is an awfully strong covalent bond. All right, so let's look at some examples. Here are two well set up reactions that have a good chance at achieving a favorable equilibrium. In the first case, we're breaking carbon-nitrogen bonds as a cost, okay, but we're making a carbon-carbon double bond, or at least the pi bond of the carbon-carbon double bond. That may not in itself be worth that much, but look what else we're making. We're making the molecule nitrogen. Now, we just finished saying that that is a molecule with an extremely strong bond, right? An extremely negative heat of formation. So that's a reaction that has a good chance of working. Okay, it's well thought out, it's well set up. So is the lower one. Okay, in the lower one, we're breaking a weak carbon-bromine bond. You can go back to that table and check. That's a relatively weak bond, and what we're replacing that with is a stronger carbon-carbon bond. Not only that, but we're incorporating a very stable carbonyl, carbon-oxygen double bond into the molecule. So that has a very good chance of having favorable energetics. But remember, that's not the only parameter for a desirable reaction. Okay, these reactions, on the other hand, are probably not worth our time in the lab, right? In the first case, now you don't see this in the bond energy table, but remember, I think we've mentioned this several times. That's a benzene derivative. That's a benzene ring in the left-hand reactant. And notice that we are destroying or disrupting that benzene pi alternating single double bond ring system in making the product, and that's a Diels-Alder reaction, which is shown there, which is a cycloaddition reaction, which is a terrific reaction, but just not with a benzene derivative. Okay, because again, you're now asking the system to disrupt an extremely happy stable benzene molecule with its aromatic stabilization to form two standard carbon-carbon bonds. You're also disrupting the conjugation in that alkene partner, which has now been destroyed in the product. So this is a reaction that has energetics that are very unfavorable. What about the lower case? Again, in the lower case, okay, you're replacing a very happy, very stable, very strong carbonyl bond with two very weak carbon-bromine bonds. So these are examples of reactions that are probably not going to work out energetically. The second parameter that we listed for desirable reactions, and by the way, before I get on to kinetics here, let me just say that please realize I am not saying that it is impossible, okay, to run a chemical reaction, perform a chemical reaction, an organic reaction with unfavorable energetics, right? With a positive delta H or a positive delta G. We're not saying that at all, okay? This is done every day. But just realize that if you are contemplating a reaction that has unfavorable energetics, that's endothermic, right, or endogenic, this means that you will have to continually supply external energy, heat, light, throughout the course of that reaction to pump products to reactants. Okay, this is why we vastly prefer exothermic reactions, which we call spontaneous, which is a very bad term because they don't just start on their own. They have to be pushed up past the top of that energy curve to the transition state, and then yes, they do spontaneously fall to products without any additional input of external energy. So that's preferable certainly to a continual supply of external energy, but it can be done. It's done all the time. Electrolysis is a perfect example of unfavorable energetics that are pushed throughout the reaction by what? By an electric current. Okay. All right. Now, that second category, you can have a perfectly favorable, energetically favorable reaction, and have it simply sit there and not do anything. And why is that? Right. Here's an example. When you operate your car, of course, unless you have an electric vehicle, and they're becoming more and more popular, which is terrific environmentally, but most of us have a gasoline, have an internal combustion engine, and so we know that that the gasoline in our car is highly combustible. In fact, one has to be very careful handling it. It can cause explosions if not handled properly, right? But nothing happens to the gasoline in the tank of your car. It simply sits there, and it's certainly not reacting. You wouldn't want that to happen unless you do what? Unless you spark it, right? That's why you have spark plugs, right? So what we're saying here is that just because a reaction is energetically favorable, where there's a big difference, say, between the reactant energy and the much lower product energy, doesn't mean the reaction will happen at a satisfactory rate. It depends on the height of that activation barrier, right? So in this case, we have two reactions, orange and pink. They both have the same energetics. They both have the same delta H or delta G, the difference in energy between the two lines. Okay. However, the orange reaction is a reaction that you would want to run in the lab because it's going to happen in a reasonable time frame. The pink reaction is a reaction that you would not want to run in the lab because even though it has the same favorable energetics, okay, that much higher barrier is going to require much longer reaction times, or as well as, right, more extensive energy input to push the molecules up that much higher barrier before they spontaneously fall down to product. Okay, to kind of wrap this up, remember we talked about chemoselectivity, regioselectivity, stereoselectivity. I want to show you two examples. One, a reaction that is well thought out in terms of these considerations, and one that is not well thought out. So the upper reaction is what type of reaction? It's the epoxidation of an alkene. Notice that there are two alkenes in that reactant. But if you studied alkene epoxidation, then you will have learned, and you will learn this, you will have learned that the more substituted the double bond, the more electron rich it is, and the more electron rich it is, the faster it reacts with the epoxidizing agent, so that you can certainly epoxidize that tetrasubstituted alkene in the cycloheptene ring in the presence of that monosubstituted side chain alkene. That's not difficult to do. Not only that, you do achieve stereoselectivity because the epoxidizing agent comes in from the face of the molecule or the alkene, which is away from the chain. Contrast that with the lower reaction. Now, in the lower reaction, you are wanting to do a chemical reduction, a hydride type reduction of the carbonyl. You have a molecule that has two carbonyls. That CHO is an aldehyde carbonyl. You also have the methyl ketone in the molecule. Now, normally, aldehydes react a lot faster than ketones. So normally, your planning would be pretty good, right? You can generally react or reduce an aldehyde in the presence of a ketone without touching the ketone, right? As long as you adjust the stoichiometry of the hydride reagent. But you have to look at other factors in the molecule. And in this case, your aldehyde is highly sterically hindered. Do you see all those groups around the aldehyde, the CHO? Okay. Whereas your ketone is waving out there in space, perfectly accessible. This is going to be a very, very difficult, if not impossible, selectivity to achieve. Not well planned. All right? Okay. That's all I wanted to say about energetics and kinetics. Just some again, real basic considerations. All right, but you know, we want to spend our time in the lab efficiently, and the planning is real important. And you want to give a proposed reaction, especially if it hasn't ever been done before, and that's what original research is. You want to give it every possible chance, and these are the considerations, as well as others, that one has in planning out desirable, efficient reactions.